Thank you. I'm Lukas Rambold from HBI, and I present to you AirTied. In AirTied, we produce structures like this tower using this device. So AirTied at its core has 4 main operations. So the machine has 4 operations. So we use inflatable tube that we unroll. We can hold onto the inflatable tube, that we call bookmarking. Then we can add ties to multiple layers of inflatable tube. And finally, we can eject it from the machine for the user to inflate it later. So this is how it looks in real life. So here you can already see the unrolling. Now this was a bookmarking operation with these bookmarking slots. And now the tying device comes in, squishes the material together, and adds this wire tie. And when you do more of this, you end up with this deflated tube that becomes a truss structure once you hook a compressor to it. I don't know whether you've been in this situation, but yesterday night I needed to suspend a kind of heavy, like a 30-pound object in the demo reception. And usually, so the main technique to do this would be trusses. So trusses are kind of used everywhere. They're used in architecture for these high voltage pylons or space exploration applications. The key ingredient to trusses is that they get rid of bending moments. And only reduce the forces to compression and tension forces. So the overall structure is very sturdy. And we at Hasselplatten Institute explored truss structures in the past a lot. So there's Truss Fab in 2017, Trussformer 18, and in Trussulator at UIST 21. But now these previous works were already were manually assembled, and we now want to automatically assemble these structures. And related work, there are 2 main approaches how this has been done. The one is using prefabricated truss voxels that are built into larger truss structures. But for my demo reception, essentially where I would need these voxels already, and they are kind of big, so I can't really put it on the plane. And then we have the other approach. So this is building an architectural column from epoxy-soaked yarns, carbon fiber. And they are hanging from this contraption, and this is kind of a big scaffolding. So you need kind of a big structure to build a big structure, and this is also kind of a no-go for the demo reception in that case. So we need something that uses neither building blocks or scaffolding, and this is where we draw inspiration from related work in the inflatables. Inflatables are awesome. They have no building, like fundamental building blocks, and have no scaffolding, but right now they are not really sturdy, so this would topple over quite quickly. So the question is how to get kind of the best of both worlds together, and this is what we do in AirTied. And here, if you haven't seen the demo reception, this is what the final result looks like. And yeah, we had it propped up to produce these sort of structures. So the core insight that AirTied builds on is that this is, for example, a tetrahedron, and we just have to produce the nodes. So AirTied is all about making these connections. And it's already a tetrahedron, even if it's deflated. It's topologically a tetrahedron. So this way, we can produce the topology in a small deflated state and then blow it up. And this way, we get kind of this scale effect. Let's look into how AirTied accomplishes this. So I already mentioned we have kind of 4 fundamental operations that we have to implement. And this is what the machine looks like. So we have this metal ring, and in the middle you have the roll of inflatable tube, which sits on these rollers. So they are there for unrolling. And then we have these bookmarking slot components that are there to hold onto tube and store it, and then also aid the tying process. And we have 5 of them in our implementation. In the middle, you can see this carriage, and this has two functions. So on the one side, we have the tube pusher, which guides material around and inserts it into the slots. And on the other side, we have our tying device that produces the ties in the end. And this is how you then, when inflating, you get these structures out. AirTied also automates kind of the fabrication process, but we also aid during the designing process. So we built kind of a software pipeline based on Truss Fab to guide kind of, to make it very easy to also design structures for the system. And in the system, so it's a SketchUp plugin, and you would have this Octa tool, for example, and you, with a Minecraft-style interaction, you can click together octahedra into larger objects. What we added now for AirTied is that when you try to create a geometry that would not fit on the machine, we get like a real-time feedback that this would exceed now the capacity for slots that you have on the machine, and we compute kind of what the machine should do in real time in every interaction. This way we can also show where double edges which will show up because that are necessary to produce the structure. And finally you get a preview of how much tube you will need and how much it costs. After the user designed the structure, our algorithm takes over and generates the instructions for the machine. So the idea is that the user put in some target shape, and we need to map the tube onto this target shape. What we use for this is something called Fleury's algorithm, and we build on it for our use case. So Fleury's algorithm works in a way that it starts at some node and it walks down the object step by step. So here we choose this edge because this reduces the number of memory slots that's needed. I mean, in this it doesn't really matter, but in general it does it. And then it traverses the structure. However, in Fleury's algorithm, you run into this issue. So here you are in a dead end, and then you're still missing kind of this last edge. And what we are doing is we essentially doubling one edge to still be able to complete the structure. And this works for any structure, surprisingly. The other thing the algorithm does is it prefers paths that reduce the number of slots. So this edge, if we choose this edge, we use 4 slots, and this edge is 3 slots, so we do the other edge. And lastly, if you do this naively, you can run into situations like this, where you have the right octahedron, but it's topologically tangled up, and you actually want this. And we compute the fabrication result in the background, and when we detect the tangling, we retry a different approach. We evaluated our system by producing multiple structures. So this is a 6-meter tower that we actually had to shorten for the demo last night because it wouldn't fit in the room. And then we had we played out the scenario of like a do-it-yourself water park with a goal and a chair, and then you can have fun, HPI essentially. We measured the fabrication times, and we are between 15 minutes and 33 minutes, so this is quite fast compared to Truss Fab. And we measured the success rate. It's a 97% success rate per operation. So to conclude, so this is what saved my life last night, essentially. So we could prop up the structure, and on the way back, so we didn't actually produce this here, we shipped it in, but this is also a kind of cool property of the system that you can actually do this. So this whole tower fits in a suitcase, and now we can take it home essentially on the plane and have it a portable tower essentially. And when we get back home, I'll take a set of pliers and just cut the ties and then roll it up for the next project. So you can also reuse it, and I will work on actuation and kind of large-scale soft robotics next, which is my future work. I would thank to all my amazing co-authors to help with this work, and happy to take your questions.
Liang He from Purdue University. Very nice talk, and I really love the machine. I also appreciate that it's portable. So my question is very simple. Did you try any different size of the tube, like the width of the tube? So, because most of the applications are large-scale applications, did you try any like smaller scale?
We started out with smaller scale, so the machine right now cannot use different diameters, but the whole approach totally works with different diameters, so you can scale it down and do like, I don't know, 3D printing size structures essentially. Or you can also double the diameter, and then you get much more like larger structures essentially out. Yeah, but you would need to redesign the machine to accommodate for this right now. Yeah.
Thank you.
Hi, Koya from the University of Tokyo. So I think I still don't quite understand the mechanism. So is it possible to fix the folding angle of each hinge, or do you need to fix all the nodes to finalize the shape?
So if I understand the question correctly, so the mechanism creates the nodes.
So is there any way to fix the folding angle of each hinge?
No, it doesn't care about the folding angle. We assume that the structure is like a rigid graph.
Yeah, okay.
And therefore the folding angles are defined by the structure itself.
I see, thank you.
Hi, I'm Sophia from Stanford. Great talk, it was very cool. I'm wondering if you considered integrating any sense of physical viability into your design tool for users. I can imagine a user maybe accidentally designing a truss that's meant to be load-bearing but can't bear the load properly, or is maybe off-kilter somehow.
Yeah. So we didn't include it in the tool right now, but I think that's actually kind of, even without explicitly checking for it, I think it's actually an advantage that the structures are so light, because we produced this gigantic pavilion from Truss Fab, and it's always a little bit scary if people walk under it sometimes, or shake on it, I guess. And for this, even if it would collapse, it's still it's fell on me several times somehow, and it's totally fine. I think, yeah.
Thank you, yeah, it sounds low stakes, luckily.
Yeah. So the tower is actually only 6 kilograms, so it's very light, yeah.
Cool, yeah, thank you.
Hi, really loved your talk. This is Elizabeth, also from Stanford University. I was curious if you could talk a little bit about the, payload versus, you could say pressure that you have to put into it, and how that changes based on what your algorithm is of what you're doubling up in all of those natures.
I didn't understand the last part.
Sorry.
The last sentence.
So the algorithm we're using of deciding what edges to double up would also affect how much weight that the truss could hold and the integrity of that truss. So I was curious, do you take that into account when you're deciding your algorithm of which paths you're choosing, and as well as what the payload is to, I guess you could say, the pressure that you have to put into the truss?
Yeah, so the path per se doesn't really influence the payload. I think when you want to design very stable structures, you want to have short edges essentially, because the main problem is buckling, and buckling is essentially goes down by quite considerably if you have short edges. And right now we are inflating the tubes with 0.2 bars, and we get so right now they buckle at 30 kilograms, a 1 meter beam, when it's perfectly aligned, I guess. Yeah.
Thank you.
Hi, Alejandro from UCSB. I love the project, love the presentation. Was telling my partner yesterday that I wish I've had this as a kid. I would take in my parents' living room over. With that in mind, have you thought of any interaction of possible changes to the tool to allow for editing or like changing the nodes positions? I know that right now you have like a tie rope or like a wire, but maybe some kind of color that you can untie and shift around to like kind of like have an editing possibility of the structure, and you can play with it a little bit more.
Yeah, so I mean, some of the editing capability was essentially at the demo reception. I mean, shortening the tower. You essentially, I mean, if you figure out the path, you can pull through the tie, and then you make some segments shorter than others. Okay. From supporting this from a software side, right now the tool only like supports moving nodes, I guess, and then you would need to refabricate.
Thank you.